pair, so what happens to that fourth electron? It goes down. Now you have a spin pairing where you have to put two electrons very close together. Electrons don't want to be close together. So by putting that fourth electron down in the same orbital as the third, or as one of the ups, you cause a repulsion to occur. Does that make sense? So electrons repel each other. By causing that fourth electron to be a down electron in the same orbital, you have a repulsion that occurs which causes the electron to swell up again. Okay? And then once again the pattern holds again. As you're adding electrons, you're still adding electrons and protons, the atom will get shorter. So it goes small, 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 up electron, small, 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 small. Make sense? Yeah. Okay. So that's why there's a gap there. And there's a whole bunch of gaps in the D block because the D block electrons are what we call multivalent in that their D block electrons can move all over the place. And we'll talk about why that is in the next unit. We'll talk about why the D block electrons are so goofy and how they can just migrate all over the place with the S's and the P's. So we'll deal with that next time, or next unit. Okay, so why is it that the atom gets bigger as we go down the periodic table? Exactly, more shells. So as we go across the periodic table, we're going new electron, same shell, new electron, same shell, new electron, same shell, new electron, same shell. And then as we go down the periodic table, new shell. Okay? That new shell is very repelled from the inner shell, and so it gets bigger. And there's this thing called shielding, which we're not going to go into, but shielding basically says that those inner shell electrons shield the outer shell electrons from the nucleus attraction, but we're not going to go into that. If you want to learn more about shielding, you're welcome to take Chemistry AP. Okay, next. This is ionization energy, which is the energy required to remove an electron from the atom. Okay. In other words, the energy that us, at the macro level, have to exert to pull an electron off at the atomic level.
Hold on.
So, remember the whole Pokemon idea? So the Pokemon idea is like if you have 110 cards you need to get and you have 109, are you going to want to trade away one of your 109 if you're so close to getting a set?
No, you just buy 4 new ones.
No. So you're going to work really hard to get that one electron. That's going to be the next unit or next we're talking about. But as far as electrons you have, if you almost have an octet, you're going to work really hard to keep that octet, which means it's really, or keep that almost octet. Which means it's really hard to take an electron away from fluorine, chlorine, bromine, and iodine because they're so close to having an octet. And which atoms have the highest ionization energy? The noble gases, because they've got their octet. If you've got your whole set of Pokemon cards, you're going to work really hard not to lose any. So, yeah, if you've got all 4 tires, you're going to work really hard not to lose one of your tires.
Bro, all you do is buy Charizard off eBay.
But if you've got 3 tires, you're going to be like, I only need 1 more tire. Okay, does that make sense? So that's the basis of ionization energy. It's energy that you and I have to use to pull an electron away from an atom. If an atom, as the atom gets closer and closer to an octet, it becomes harder and harder to pull electrons away. Now, when you get to this side, you have extra electrons. They're not just going to give them up, but they're not going to hold them very strongly. And as you go down the periodic table, what happens to the atom? It gets bigger. And this is the next part of Coulomb's law, which I'll reveal after I answer Cameron's question. That was the question? Okay. So the next part of Coulomb's law is there's over d squared. Over d squared, which tells us as you get further from the nucleus, the force of attraction goes down. Okay? It's harder for the nucleus to attract the electrons when they're really, really far from the nucleus. So as we go down on the periodic table, we're adding shells. Those electrons are further and further away. It's easier for us to remove them when they're further and further away from the nucleus. Okay, how are we doing so far? Cameron?
Does helium
Yeah, because it's so close. The electrons are so close to the nucleus, and it's got a filled orbital. So yeah, helium is the highest. All right, the next property is the most important. I think it's the one I'm thinking about. Yep, electronegativity. Electronegativity is take all of the dozens of properties that atoms have, squish them together, and assign them a number. A very simple number from 0 to 4. That is the strength of that atom to gain or hold its electrons. And it's going to be the most important property that we use in the next unit. Okay. If you like a number, or you like a definition, it's the ability to attract electrons. Electronegativity is the single most important value because it basically takes a whole bunch of properties together and simplifies them into a simple number from 0 to 4. How strongly does that atom want electrons? And because it's so simple, it's what we use all the time after this unit. Okay. Which atoms are not on the table?
All of them.
Noble gases.
The noble gases are not there because they have an electronegativity of 0. They don't want any more. They got their electrons, they're happy, they don't want any more. Which atom has the highest electronegativity?
Fluorine.
Fluorine. Yeah, fluorine has the highest electronegativity. It's small. It's almost got its octet. It's only one electron from looking like neon. It's almost got an octet. It's got a very, very high electronegativity. Now what this means is kind of interesting. If you put fluorine, which has 7 electrons, and you stick it next to sodium, which has 1 valence electron, guess what fluorine does? Yeah. Fluorine mugs sodium and takes its electron. So then fluorine has 8 electrons, which makes it happy, but sodium's also happy because now sodium has 8 from the inner shell. So fluorine is extremely electronegative. If you put it in the presence of sodium, it's going to mug sodium and take that electron. But something interesting happens if you put two numbers that are close together. If you take that same fluorine, which has an electronegativity value of 4.0, and you put it in the presence of oxygen, which has an electronegativity of 3.5, they're going to start fighting. And if you drop an electron in between, guess what happens? Oxygen says, I want the electron. Fluorine says, I want the electron. And what they do is they will share the electron, but the electron will spend most of its time around fluorine. This is the basis for chemical bonding. The idea that atoms with electronegativity tend to hoard that electron, those electrons. If the gap is big enough, like fluorine to sodium, fluorine just takes the electron. If the gap is small, then they'll share, but most of the sharing will happen around the more electronegative atom. Does that idea make sense?
Yes.
Because it's kind of a weird one. It's the basis for the next unit. So.
It does.
Okay, cool. And as we go down the periodic table, why is it that we go down the periodic table, the electronegativity gets smaller? Because the shell is further from the nucleus. Each shell is further from the nucleus. So bromine and iodine, they still want to fill their shell, but those shells are so far from the nucleus, it's harder for the nucleus to actually fill those shells. Okay, give me a thumbs up if this idea makes sense.
Thumbs sideways.
Okay, give me a thumbs down if you need to go over it again.
Nope.
All right, moving on. Ionic radii. So if atomic radius is how big an atom is, what's ionic radius? How big an ion is, right. And here's the thing about ionic radius. It's probably the simplest thing in the world.
Really?
Yes. And I'll tell you why.
Okay, go.
If you add an electron but not a proton, if you add an electron but not a proton, what's going to happen to the size of the electron cloud?
It's going to get small. Bigger.
It's going to get bigger, yeah. Because remember, if the first part is opposites attract, the second part is
Repel.
likes repel, similars repel. So if you add just an electron to an electron cloud, the whole cloud is going to repel and it's going to get bigger.
Much.
Does that idea make sense? So if that makes sense to you, it should be obvious that anions, which are the name for negative ions, are always larger than their neutral atom. Okay? If an electron is added to chlorine, the chlorine becomes an anion, and an anion is always larger than a neutral atom. Because that electron got bigger. Made the whole cloud get bigger. So hopefully that makes sense. If the first part is opposites attract, the second part is likes repel, electrons are similarly charged, by adding an electron into the electron cloud gets bigger. Now, the reason cations, and I know you're going to be fun and fancy and go, let's call it cation, but it's pronounced cation. The reason a cation is always smaller, why? Same number of protons. If you take away an electron,
If you take one away, then it's smaller because it's not there.
and what is there less of?
Electrons.
Starts with an R.
Radiation.
Repulsion, right. There's less repulsion, less repelling. Less repellitude. Okay, so if you remove an electron from that electron cloud, there's less repellitude, less repulsion, and that electron cloud is pulled towards the nucleus with a greater strength because there's fewer electrons pushing against each other. And here's the best part. Sometimes, as in the case of sodium, if you remove one electron from sodium, what do you remove the whole of? You remove the whole... Okay, let's see if you understand. You remove the whole what? You remove the whole... Starts with a shell and ends in where you're going to go if you don't accept.
Shell.
Shell, yeah. Shell. So if you remove...
Oh my god.
If you're... Yeah, good. Some of you... Let's see how many people are paying attention. If you remove an electron from sodium, sodium only has one electron in that outer shell. You remove that electron, and sometimes the whole shell just disappears, making the atom much, much smaller. Okay. Does this make sense? Okay, question?
Like non-metal and metal atom?
Absolutely. Non-metals only take electrons, except for metalloids, and metals only give up electrons. Part of what makes metals metals. Part of what makes non-metals non-metals. But we'll visit that in the next meeting. Actually, the next day. I think we'll talk about it next time. Okay. Give me a thumbs up if this idea makes sense. You give me a thumbs up, a thumbs down if you need to go over it again. Okay. Now the next thing we're going to do for the next few minutes, and we're going to talk about groups and their properties. Actually, no, we're going to run out of time, so we'll talk about that next time. What we do need to talk about is oxidation. And this is huge. Where's my green laser? Where did I put my green laser? Okay. So follow the little green dot to the periodic table. Okay, valence electrons. Everybody following the little green dot? Hi, little green dot. Okay. Lithium's group has one valence electron. Beryllium's group has two valence electrons. If lithium's group is going to get an octet, what is it going to do with this one valence electron? It's going to lose it. An atom that loses an electron has a charge of what? Positive 1. On the other hand, fluorine's group wants to do what to gain an octet? Gain one electron. An atom that gains one electron has a charge of what? -1. The stable ion of all the atoms in fluorine's group is -1. Because it gains an electron, becomes -1. Oxygen has to do what? Gain 2. The stable ion in oxygen's group is -2. Fluorine has 5 valence electrons, nitrogen has 5 valence electrons. What does nitrogen want to do? Gain 3. So if nitrogen gains 3, it has a charge of -3. And here's the pattern. Group 1 has 1 valence electron. They lose it for a +1 charge. Beryllium's group, +2 charge. Boron's group has 3 valence electrons and it loses it for a +3 charge. Fluorine's group has will gain 1 electron for a -1 charge, oxygen -2 charge, -3 charge, and then carbon. Carbon in carbon's group, silicon and so on, have 4 valence electrons. They have options. They can lose 4 for a +4 charge, or they can gain 4 more for a -4 charge. So here's the pattern of oxidation. -1, -2, oh, sorry, +1, +2, +3, plus or -4, -3, -2, -1, 0.
Let's see it.
+1, +2, +3, plus or -4, -3, -2, -1, 0. Okay. If you can see that in your head, give me a thumbs up. If you need me to go over it again, give me a thumbs down. Okay. If that is the case, and there's 90 seconds left in class, what is the common ion, with a show of fingers, 1, 2, 3, -1, -2, what is the common ion of calcium?
Oh.
Calcium's right up in there. So show me with your fingers what it is. I'm seeing some 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. Yep, 2, good. And what is the common ion of nitrogen? Nitrogen's right there. I'm seeing some 3s and -3s and -3s. Should be, boom, -3. Okay, nitrogen and nitrogen's group should be -3 because nitrogen has 5 valence electrons. It needs 3 more. Okay, I will see you tomorrow.